Now, why isn't the empty or null set a vector space? Well, in order for a set to be a vector space, it must fulfill all 5 of these properties. The empty set, or the null set, fails at 1 out of 5 of these properties. Can you figure out which one it is? I encourage you to pause the video and give it a try. Okay, so I'm going to assume that you tried to do it, and now let's cover which one it is. So is the empty set commutative? Well, let's read the definition. U plus V equals V plus U for all U and V inside uppercase V. In our case, uppercase V is the empty set. Okay, that's the set we're working with. So now you might be thinking U plus V equals V plus U. Well, there are no U and V and U inside the empty set, so it fails at this. But that's not true, because it says this has to apply for all U and V inside the empty set. But since there are no U and V inside the empty set, it doesn't have to do this, right? It does this 0 times, and there's 0 elements inside of it, so we can check this one off. Now, associativity. Does it fulfill this? Well, U plus V plus W equals U plus V plus W, and A times B times V equals A times B times V for all U, V, and W inside an empty set, and for all A and B inside F. Now, once again, this gets fulfilled the exact same way we did for this one up here, because there are no V, U, and W inside the empty set, so this is fulfilled automatically. Now, the additive identity. I'm just going to go out there and say it. This is the one that doesn't fulfill. So we're going to skip this one for now and do these two. Now, once again, these two are fulfilled the exact same way as the other ones. For every V inside the empty set, there exists a W inside the empty set, such that V plus W equals 0. Well, there doesn't exist any V inside the empty set, so it doesn't need to exist any W inside the empty set, so we can check that one off. There exists the exact same amount of V's as there does W's, right, in this definition. Then, once again, it's the exact same way for the distributive property. For all U, V inside the empty set, there are no U and V. So, once again, we can check this off. Now, let's go to the additive identity. There exists an element 0 inside the empty set, such that 0 plus V equals V for all V inside the empty set. Well, there doesn't exist a 0 inside the empty set by definition of the empty set. So therefore, it cannot fulfill this definition because there is no element 0. So it fails the additive identity. And that is why the empty set is not a vector space. Thank you for watching. Let me know if I say anything wrong or if you have anything additional to add. Have a great day.